So we're going to do some examples of proving smoothness. Now, under the assumptions that every one of the functions I'm going to be talking about are asymptotically non-decreasing, which should be the case for constant functions, logarithmic functions, and polynomials, I'm going to be working under the assumption that all we need to do is prove the second condition, which is really the exercise that I tend to focus on. For example, a constant function like this, f of 1 is equal to f of 2, right? And f of 2 is equal to f of 3. And so on, because it's always independent of the input. It saves us a lot of time when we actually want to prove statements like this. However, in the other cases, I want to leave that exercise to other videos. So I'm going to focus only on the second condition, which is primarily the exercise when we're trying to prove smoothness of a function. At least in the purview of many of the classic functions that usually people are interested in computer science, which we already usually are well known to be asymptotically non-decreasing. So let's do a proof for this. You're going to see that it's not very different from doing a big O claim proof that you're used to from these videos. So here we go. So what are we going to do? We just say what we're going to do. Remember, we're trying to prove a big O claim. So we're going to say we find constants. We find constants C and N0 such that for all n greater or equal to n0, f of 2n is less than or equal to c times f of n. That's what we're really trying to prove. I'm just substituting in our definition, right? But what is this? What is this? Well, when we define n in this way, it's no different than me writing the following: that d is less than or equal to c times d. This might look familiar to some of the earliest examples I've done. I'm just going to pick c is equal to 1. You might ask why? Well, you'd agree with me that if I make this 1, then d is less than or equal to d, which means that it has to hold because of equality. So pick c is equal to 1. Then notice that both sides of the inequality are equal for all n greater or equal to 1. So what should I pick for n0 then? Well, it doesn't really matter. I just pick one. So I'm going to just choose n0 equal to 1. Therefore, by the definition of big O, D is big O of D, and function f is smooth. Now, it's worth noting that this last sentence isn't really about the original claim. I'm going to put that in parentheses just for your context. So really the sentence is going to be ending here, but I just want to emphasize that because we know constant functions like this one are in fact asymptotically non-decreasing, that they must also be smooth.